We see water boil almost every day. But have you ever wondered what's really going on inside that kettle? The physics is weirder than you think. Matter exists in different phases, or states. In a solid, molecules are locked in a rigid lattice. In a liquid, they're close but can move past each other. And in a gas, they're far apart and move freely. When we add heat to a solid like ice, its temperature rises. The molecules vibrate more and more intensely. This seems straightforward, until we hit 0 degrees Celsius. And here's the first weird thing. As the ice melts into water, the temperature flatlines. It stays locked at 0 degrees, even as we keep pumping in energy. This energy, known as latent heat of fusion, isn't increasing the kinetic energy of the molecules. Instead, it's being used entirely to break the bonds of the solid structure. Once all the ice has melted, the temperature of the water begins to rise again. The added heat now increases the water molecule's speed, and the temperature climbs steadily. But then we reach 100 degrees Celsius, and the same weird thing happens all over again. The temperature stops rising completely. This is boiling. Just like with melting, the enormous amount of energy, the latent heat of vaporization, is used to break the bonds holding the water molecules together in a liquid, not to raise the temperature. So, what's the difference between this and simple evaporation? Evaporation is a surface phenomenon. Boiling is a bulk phenomenon. It happens from within the liquid itself. But this leads to the second weird question. If boiling starts from within the liquid, where do the bubbles actually come from? Creating a bubble from nothing is incredibly difficult. The answer is nucleation sites. Tiny imperfections on the surface of the container, or even dissolved gas pockets in the water, provide a starting point for bubbles of water vapor to form and grow. Without these sites, you can get a dangerous phenomenon called superheating. In very clean, smooth containers, water can be heated past its boiling point without actually boiling, because the bubbles have nowhere to form. Any disturbance, like adding a spoon or even just shaking it, can then trigger a sudden, explosive boiling event, as all that stored energy is released at once. It's incredibly dangerous. The final piece of the puzzle is pressure. The boiling point of 100 degrees is only true at standard sea-level atmospheric pressure. Change the pressure, and you change the boiling point. At high altitudes where the air pressure is lower, water boils at a lower temperature. This is why it takes longer to cook food on a mountain. The boiling water isn't as hot. Conversely, a pressure cooker does the opposite. By increasing the pressure, it raises the boiling point, allowing the water to reach a much higher temperature and cook food faster. All of this behavior is beautifully summarized in a phase diagram, which maps out the state of a substance at any given temperature and pressure. Boiling is just crossing one specific line on this map. So, boiling isn't just hot water. It's a precise, energy-intensive process where temperature freezes, bubbles form on tiny imperfections, and everything depends on the pressure of the world around you. Next time, we'll dive into one of the most famous and misunderstood ideas in all of physics, Maxwell's demon. Join me then.